Good morning. Here we are, the physics video lecture, Physics 105B, video lecture 21. So I'm going to make this another special topic before we jump into the full rigid body motion topic that we were at. I had some requests about the double pendulum with the electromagnetic coupling, okay, with the charged double pendulum. And I decided to go ahead and do it really thoroughly because there's a lot of interesting stuff going on there. So we'll do this totally thoroughly. Hope we can pull it off. Okay. So this special topic is just to go through that double pendulum. So let's just call that the electromagnetically coupled pendula, and I'll try to get a good sketch here that we can work with. Yeah, we'll make a big sketch here. Okay. So we have the two pendula, and in their totally relaxed equilibrium state, they're right here. Okay, there we go. We have a separation distance d, and we can of course swing these up, say up to here, and then we would have a phi sub 1. I'll go ahead and make this the solid line. Okay, and we've got M in the middle, and L. Okay, and then likewise over here, this one could swing up even more, and then we'd have a phi sub 2, L, same mass. So I've got these little arcs. And I can even put a coordinate system y and x like that. Okay. What else do we have here? We have charge, Q1 and Q2 on these things. Q sub 2, got the separation distance d. So they're hanging there. Okay, that's fine. Now, as far as the Lagrangian goes, T minus U, what we're going to do is the small oscillations formalism on this thing. So we need the kinetic energy, and that's no problem at all. That's 1/2 ml squared phi1 dot squared plus 1/2 ml squared phi2 dot squared. Okay. Potential energy is a little more interesting, and I want to do this one as thoroughly as possible. So potential energy, we'll just say mgl 1 minus cos phi1, because I'm taking literally the origin right here, okay, cos phi1 plus mgl 1 minus cos phi2 plus, I could call the next part that's going to be a little more difficult, U sub electromagnetic. Okay, so we need the electromagnetic part of the potential. These are the two gravitational potentials. And the electromagnetic part, I'll go ahead and write up here. Yeah. So U sub electromagnetic is going to be equal to alpha over R, comma, alpha is equal to Q1, Q2 over 4 pi epsilon naught. And so alpha can be positive or negative, right? If we have opposite signs, alpha is negative, like signs on the charges, alpha is positive. Okay. And what about this R, this separation distance? What I do is I often just cut to the chase, but let's go ahead and write this thing down really thoroughly. It's the separation distance between the centers of these 2 point masses that have been charged. So we could say it's x2 minus x1 squared plus y2 minus y1 squared, square root of that. So that's the full, Pythagorean theorem in there. Now let's see what we have under that square root. X2 is d plus L sine phi 2. So we have d plus L sine of phi 2. Okay. And then x1 is L sine of phi 1. So minus L sine of phi 1 squared. And the y2 minus y1, they both have the same form. You have L cos phi 2 minus L cos phi 1 squared. Okay. Now if we had to take 2 derivatives of this in the denominator and so forth, things would not be pretty. But let's go ahead and look at this a little more. We want to use the small angle approximation. So I'm going to make an approximation here, and I'm going to write small angle. I'm leaving room here so I can monkey around underneath here if I need to explain this a little more. Now, the cosine is 1 minus, actually, did I write the 1 minus in there yet? Yeah, I'm going to. Since I put my origin there, I'm not going to skip any step. So it was L times 1 minus cos phi 2 minus L times 1 minus cos phi 1 quantity squared. Okay. Now here's what's going to happen. We're going to have, since we're looking for small angles, we can expand these things here. Strictly speaking, we would have U electromagnetic. Now it's been well defined in terms of phi 1 and phi 2. Here, let's even write that. U electromagnetic of phi 1 and phi 2. Yeah, let's run through this now. Phi 1 and phi 2. U electromagnetic is alpha over R. Alpha is Q1, Q2, 4 pi epsilon naught, just constants. R is this thing, and it's in that denominator. Okay. So what we would be doing in the small oscillations formalism is taking first derivatives for equilibrium and second derivatives for the constants in the K matrix. So let's recall U is the entire thing here. We need du d phi 1 equals 0, du d phi 2 equals 0. For the equilibrium positions, phi 1, phi 2 at equilibrium. And then also we need d squared u d phi I d phi k at phi 1 comma phi 2 equilibrium positions. Right? These are constants the reason I have to, how about I put a little star there? Or, yeah, put stars there for the equilibrium position. Okay, so that's our program, and in this form it's well formulated. Remember, those will be in the K matrix. These two are already in the M matrix, no problem there. But none of these things can be done exactly, okay? And yet we want to get a good answer, okay? So a lot of interesting things are going to happen. But make sure we have everything, because my next approximation is going to be drastic. So equilibrium is going to be a small angle. Here's another point. Equilibrium, we'd like for it to be phi1 and phi2 equals 0, but it's not going to be 0. Okay? Because these things are charged and they're either slightly attracting each other or slightly repelling each other, even in the small angle approximation. So we'd like to just declare these things to be 0, right here, 0, but they're not. So that's also an important note. Phi1 star and Phi2 star are not equal to 0. Okay. And you can also see second derivatives of this thing when it's in the denominator are also not going to be that fun. Okay, so let's go ahead and discuss this point here. Since it is going to be small angle, you know, the ones and the one, they're going to go away when we do the expansion, or if we did the expansion. So we would have cosine is 1 minus, right? So that gets rid of that 1, and the next term is phi squared over 2. Same here, okay? So when you have phi squared, that's going to be much, much smaller than the first terms here that are linear in phi. Okay, the sine starts out as sine of phi is equal to phi plus stuff, and this one starts out as phi squared. So in a small angle approximation, we can ignore these. What that means for this picture up here is that the angles are so small that the separation distance is essentially changed only by the x components and not by the y components. You know, that's a property of the Pythagorean theorem as well. You know, the hypotenuse and the base of a triangle like that are almost the same. Okay. So yeah, we're getting rid of these altogether. And these here, we're doing the small angle approximation, and we can now replace this whole square root by d plus L phi2 minus phi1. Okay, so this step is crucial, and it needs a lot of discussion. Because now we have something we can really work with. Okay. And what the small angle, and we're also going to require that L times either of those phis, or both of them, is much less than D. Okay. So this thing is changing a little bit. The D is dominating there. And you can see in our picture, it just means that we've got small oscillations. It's much smaller than the separation distance. Okay, okay, so now we have the ingredients to rewrite the potential energy in a more useful form, easier to use. Yeah, I want to keep that picture. Everything. Let's see. Now let's go ahead and keep the picture and just rewrite our potential energy. Okay, yeah. So even though I've made a small oscillations approximation, it's not yet the small oscillations approximation. So now U is approximated by U is equal to minus MGL cos phi1. So I'm getting rid of the constants. You know in Lagrange mechanics, constants we can take them or leave them, okay? Minus MGL cos phi2. And now we're going to say plus alpha divided by D plus L phi2 minus phi1. Okay. And yeah, we can erase all of this stuff, come back to it. Okay, good. So this is the thing we have to expand. Here's our program, and here's the object. Right. So let's talk about equilibrium next. Equilibrium. So we need du d phi1 equals 0 and du d phi2 is equal to 0. So we'll just do du d phi1. And what do we have? We have mgl sine of phi1. Of course, in the small angle approximation, we could take linear, right? We could say sine of phi1 is phi1. Won't do that yet. This no derivative there. Here we have minus alpha over d plus L phi2 minus phi1. This whole quantity squared, and the inner derivative is minus L, okay, because of the derivative with respect to phi1 down here. So times minus L. And you can see the derivative with respect to phi sub 2 is going to have this same thing with a plus L. Okay, so we don't even have to write it down right now. And for small oscillations, phi1 less than 1, let's go ahead and write this as mgl phi1 plus alpha L divided by d plus L phi2 minus phi1, the quantity squared. Okay. And we want to set this thing equal to 0, but we can't. We're going to have the same equation with a minus alpha L for the phi2. So I'm not going to write it down. Du d phi2 is the same with a minus alpha L. The point is, so we don't even have to do the sign. So we're to small angles, we're requiring small angles, but try to solve this for phi1 and phi2 at the same time. Okay, it's not going to be easy. I will write this in here, do it in red. E2 is equal to E2 less than 1 MGL E2 minus alpha L E plus L is E1 squared. Now, you can do a couple of things here. You want to solve these simultaneously. So, equals 0, exclamation point. You want to solve these simultaneously. So you add both equations, and you get rid of these right things here, and then you find that phi1 equals minus phi2. So that's one part of the result. Phi1 equals minus phi2. That's because they're either both tilted towards each other or tipped away from each other. Okay. But then if you want to find out what phi1 and phi2 are, you plug that in there, and then you're going to get a cubic. So that's not a route we want to go. So we're not stumped though, because we have, we have everything in front of us. We want these to be equilibrium at 0. We can't have that, but we still can require that they be very small, okay? And if we require that they be very small, then we can go ahead and substitute them for 0. And I'll show you how that's done. So this is a good board. I'm going to send this up. Okay, let's see what comes next here. Sure, so everything's good there. So what we're going to do is evaluate all of these expressions at phi1 and phi2 are equal to 0, okay? We're going to evaluate all derivatives at phi1 equals phi2 equals 0. In order for that to be a good approximation, we have to be able to ignore L phi with respect to D. We already required that though, okay? So require L times phi be much less than D, okay? If they're much less than D, we can neglect those in these expressions here. So let's go ahead and investigate that. Require L times phi is much less than D. That means we just end up with alpha L over D squared in expressions like this, okay? So what does this mean physically? So what does L phi much less than D mean physically? And phi be much less than 1. So what we want to know is what these two requirements, which are essentially equivalent, what they mean physically. So phi equilibrium much less than 1. What does that mean? What we mean then is that so if these things are almost approximately equal to 0, here we go. We have MGL phi1 is going to be approximately equal to alpha L over D squared. Okay. So for these to be close to 0, MGL phi1 approximately equal to alpha L over D squared, because these are small. So then we have L's cancel. phi1 is approximately equal to alpha over D squared divided by mg. We can write that way. Alpha over D squared divided by mg. And that is alpha Q1, Q2, Q1, Q2, 4 pi epsilon naught D squared divided by mg. And here's our criterion. So for those angles to be so small, here we go. The electromagnetic force, this is just the Coulomb force, is much less than the weight of our object. So the Coulomb force is much smaller than the weight, because we want phi to be much less than 1. So there's the criterion, and this one here is really going to require the same thing. So we have phi much less than d over L. D is much less than d over L, and since d over L is of order unity, we're again requiring that phi be much less than 1, which is consistent with this entire requirement. To have the small oscillations, L times phi had to be much less than d. And now we see physically, if we're actually putting these, building one of these devices, we have to have the Coulomb force be much weaker than the gravitational force, which is also completely consistent with these things just being tipped out very slightly in equilibrium. Okay. So that's how we can get around doing this thing exactly, because we don't want to do it exactly, right? It would be too complicated. Okay, so now we're ready to finish this problem off. And I should point out, if you have a decent overview, physical intuition for what's going on, you can save all of these considerations for the very end, when you've got a result. But yeah, we're going to evaluate everything at phi1 equals phi2 equals 0. And the errors that we're making are the same errors of the size if you were to expand this thing. Okay, and your L phi is a very small quantity compared to D. Okay. So the point is we have complete control over any errors that are being made. In the limit, as L phi over D goes to 0, we get exact results. Okay, good. So now let's go ahead and do those derivatives. I think we have everything up there to do that. So I'll go ahead and erase this whole thing. Okay, so we need these derivatives now. So we need d squared u d phi I d phi j. And we have du d phi 1, so we're going to have d squared u d phi 1 squared is going to be differentiating. We can definitely go with this one, no problem. So we'll have MGL, and then we'll have plus alpha L, and then we've got a minus 2 power, so minus 2 alpha L D plus L V2 minus V1 cubed, and then the inner derivative with respect to phi sub 1 is another minus L, negative L. And we'll clean that up in a moment. And we'll have d squared u d phi 2 d phi 1. So now we do this one with respect to phi sub 2. Right, with respect to phi sub 2, that one's ignored, and we have equals alpha L minus 2 d plus L v2 minus v1 cubed, and the derivative with respect to phi sub 2 just brings out another L here. And then that's going to be d squared u d phi 1 d phi 2. Those are well-behaved functions, always the case. And, oh yeah, we need the last one here. D squared u d phi 2 squared. And that one we have to work here, so we have MGL. And we'll have minus alpha L, and we'll have a minus 2 D plus L V2 minus V1 cubed, and what? The derivative with respect to phi sub 2 gives us another L. So now let's evaluate these for phi 1 equals phi 2 equals 0. Phi 2 equals 0, phi 1 equals phi 2 equals 0. We have here MGL plus 2 alpha L squared, 2 alpha L squared over D cubed. And here we have minus 2 alpha L squared over D cubed. And here we have again MGL plus 2 alpha L squared over D cubed. Good. So I think we're ready to set up our matrix and show how this is equivalent to the problems we had done before. And remember, alpha can have a change of signs, and we've figured out, is it still up there? No, I erased it, but we figured out what the conditions were for these approximations to hold true. Good. So we're talking about the eigenfrequencies, and we have the determinant of minus omega squared m plus k is equal to 0. So our matrices now, m equal to ml squared 0, 0, ml squared. And this K matrix is MGL plus 2 alpha L squared over D cubed minus 2 alpha L squared. Plus 2 alpha L squared D cubed minus, oh, backwards, sorry about that. Minus 2 alpha L squared D cubed and MGL plus 2 alpha L squared D cubed. And this is equivalent to our 2 masses and 3 springs. It's also equivalent to our coupled pendulum when they had a spring coupling them. Okay. Right, a little more complicated, but really, it's got that. In fact, in the limit as alpha goes to 0, it's just going to be the same 2 frequencies. And depending upon the sign of alpha, you'll either get an increase or a decrease in those frequencies, which is also pretty interesting. But yeah, from here you can just go ahead and do the math according to this. Okay. So I'll just wrap this up. Let's see. So what we're comparing this to is, just so this is in your notes as well, you can compare it to this Lagrangian, M, L, and L, or the 2 masses, 3 springs. This one, again, is a little more general because it has a repulsive and an attractive potential, so you can adjust alpha here, okay, the sign of alpha. But otherwise, you're going to get all the same features, the beat frequencies and what have you. You're going to get all that. And okay, I don't no longer have them on the board, but those conditions, and we saw what they were actually. I'll even put them up here as well again. So the condition was for phi, either one of them, phi sub I, had to be less than 1, and it turned out that Q1, Q2, 4 pi epsilon naught d squared has to be much less, I'll just put it this way, has to be much less than mg, which is the weight of those pendula. And so in the limit, you know, the smaller this is compared to this, the closer these approximations are to exact. And again, I want to stress that, you know, as physicists, we're able to make these approximations because we have some understanding what all these symbols mean, you know, because it would have otherwise been an intractable problem mathematically with cubics and all those other things. You know, actually worse than cubics because there were sines and cosines in there. What are those equations called? Okay. But as it is, with the with the control over these parameters, we're able to find the regime where the solution is really basic and just matches the solutions we have here and here. Okay, good. So that's this problem is really worth putting in your list of important problems because of all the judgments that are required to get to the end here. Okay, we'll leave it at that, and next time, unless I come up with another idea, next time we'll be in the rigid body motion again. Okay, see you later.